Hi, my name is Austin Rowland, and this is my Lab 5 video report. So for this lab, we were tasked with creating our own lab, and the footage that I decided to analyze was the motion of a falling slinky for this lab. And the purpose of my experiment was to analyze the video footage of that falling slinky and create a computer model that uses Python coding in order to recreate this footage. And for this lab, we will start with our fundamental principle of Newton's second law. And the main question that we want to answer is, does the bottom of the model slinky stay stationary just like it does in the video? So the fundamental principles and equations that we use for this experiment are the momentum principle, Newton's second law, velocity and position update formulas, drag force, gravitational force, and tension force, which for this experiment, we assumed this to be equal to the gravitational force while it is in static equilibrium. So here's the tracker video that I analyzed for my experiment. As you can see, it's not falling until the top of the slinky reaches the bottom of the slinky and the tension force is no longer acting upon it. So here's the time versus Y position graph. As you can see, it stays stationary up until about 6 seconds, and then it decreases in Y position. And just for reference, my Y values are negative because I set the top of the slinky as the reference point, or where he lets go of the slinky. For my video analysis, before the slinky starts moving, it's in a period of static equilibrium, and only gravity and tension act during this portion, and drag is not considered because it's velocity dependent and the object has no motion. This is caused by the tension force being equal to the magnitude of the gravitational force, and this causes F net Y to be equal to 0. And once the bottom of the slinky is moving, the tension force is assumed to be 0 because it has now reached an unstretched state. In this case, gravity and drag are the only two forces included in the second portion of this video. And since we have two different portions with different forces, the computer model needs to include two different while loops to correctly account for forces in each part. So these were my computer model initializations, set the slinky mass and the initial position. So the resting length of the slinky were both things I found online for like how long a slinky is and just how much the mass of a like generic slinky weighs. Our starting velocity is 0. Our initial time is 0 with our delta t being equal to 0.04 seconds. Gravity is equal to 9.8 meters per second squared. And B I determined was 24.5 because this is what made the final position line up with that of our tracker video. So in the first loop here on the left, you can see the mass of the slinky is equal to slinky.m for simplification of calculations. I have calculated the gravitational and tension forces and added those together to get F net. And then F net is plugged into the velocity update formula, which this answer is plugged into the position update formula. And then it adds time to update the loop to continue going. And then it graphs those position and velocity curves. And then on the second, it does all of the things that the first loop does, but it starts from the time when the first loop ends and goes until the end of the time for the total video. And it also, instead of graphing or accounting for our tension and gravitational force, it accounts for gravitational force and the drag force now. And here's the experimental versus computer model data. As you can see from that graph, so to answer the main question of this lab, the computer model and the video footage both show that the slinky remains stationary during its period of static equilibrium. And after that period of static equilibrium is when the data in the model starts to deviate from the video. These deviations may be a result of assuming that the slinky remains in a compressed form and does not have any further stretching after static equilibrium. The real slinky motion was above the line of the computer model motion in that graph. And if the slinky does stretch out again, it decreases the downward change in Y position, and that is explained through increased surface area on the slinky that is perpendicular to the direction of motion, which would increase our drag force, or the recurring tension force that would oscillate as it's pulling and pushing against each other over and over again. And both scenarios would cause the slinky to slow, which explains this smaller displacement that we can see in the graph here. All right, that is all. Thank you for watching.